Welcome to The Explainer. Today we're going to tackle a question that's so fundamental we kind of take it for granted. How do we all agree on how big something is or how far away it is? It's like this invisible language that runs the world, and we're about to figure it out.
So let me ask you something simple. How tall are you? You probably know the answer right off the bat, in feet and inches or maybe meters and centimeters. But if you ever stop to think about how a person halfway across the globe can hear that number and know exactly what you mean, that universal understanding, that's what we're getting into today.
And to really get our heads around this, let's follow a little story about a girl named Deepa. She's hit a growth spurt. She needs a new school uniform, and that simple task is about to lead her into a really fascinating measurement puzzle. So, here's Deepa. She's got to get a new uniform, right? So her mom takes her to the market. But as they're getting the cloth and then heading to the tailor, Deepa starts noticing something strange. They run into three totally different ways of measuring things, one right after another.
And this is where it gets really interesting. First, the shopkeeper pulls out this standard-looking metal rod. Then, the tailor uses a flexible tape measure, to get a really good fit. But then, her mom uses this really cool ancient method called char angula, which is literally just using the width of her own four fingers as a measurement. 3 jobs, 3 completely different ways of measuring.
And right there, that's our puzzle. You've got these modern, standardized tools on one side, and these old, traditional methods based on your own body on the other. With so many options, how can we ever be sure we're getting the right size? How do we avoid total confusion?
Well, this whole question gets Deepa and her friends thinking, and they decide to do what any curious person would do. They set up a simple but honestly brilliant little experiment right in their classroom to get to the bottom of this whole measurement mystery.
So here's the challenge they set for themselves. Measure the exact same classroom table, but they can only use their hand spans. That distance from the tip of your thumb to the tip of your pinky when you stretch your hand out? It sounds easy enough, but you're about to see the results are, well, they're pretty telling.
All right, so let's look at what they found. Anish measures a table and gets a little more than 13 hand spans. Padma gets exactly 13. And Tasneem, she gets a little less than 13. Wait a minute. Same table, 3 different answers. And the reason is so simple but so important. Everybody's hands are different sizes.
And boom, that is the big aha moment. Deepa gets it. This is exactly why we have things like scales and measuring tapes. Using your own body parts, whether it's a handspan or a footstep, just isn't reliable if you want everyone to get the same answer.
See, this whole handspan problem, it's not just a cute classroom game. It points to a huge universal truth. If we want to build things, or trade with people, or do science, heck, if we just want to communicate clearly with our neighbor or someone on the other side of the planet, we need a system that everyone can trust. We need standards.
So the solution all comes down to this one simple idea, the unit. A unit is just a fixed amount that we've all agreed on. See, every measurement has 2 parts, a number, like 13, and a unit, like handspans. The student's problem wasn't the number, it was that their handspan unit was all over the place.
So to fix this handspan problem for the entire world, we all basically got together and created the International System of Units, or as it's known, SI units. This is the modern language of measurement. It's what makes a meter in Mumbai the exact same length as a meter in Mexico City.
So for length, the main unit, the king of the castle, is the meter. And what's so cool about this system is how neatly it all fits together. For really long distances, we use kilometers. That's just 1,000 meters. For everyday stuff, we use centimeters. 100 of those make up a meter. And for tiny little things, we use millimeters. It's a super logical and consistent system for everything big and small. Okay, so we've got a handle on how to agree on the size of something. That's awesome. But that's only half the story, right? Because what happens when things don't stay still? Let's totally switch gears now and dive into the world of motion. All right, picture this. Deepa's on the bus. She looks around and to her, all the other passengers are just sitting there perfectly still. But then she looks out the window and whoa, the trees, the buildings, everything is just flying by. And this leads her to a really deep question. Are the passengers actually moving or are they sitting still?
The answer, and this is a really cool concept, is all about your reference point. Here's the secret. Motion is never absolute. It's always relative to something else. And that something else is what we call your reference point.
So get this, it's wild. If Deepa's reference point is the bus itself, well, the passengers aren't changing their position compared to the bus, so they're at rest. But if her reference point is a tree on the sidewalk, then she, the bus, and all the passengers are definitely in motion.
So an object can be both moving and still at the exact same time. It all just depends on your point of view.
Okay, so now we know how to tell if something is moving, but it turns out there are different ways that things move. It's not all the same, and we can actually sort motion into a few key types. First up, the most straightforward kind, linear motion. It's exactly what it sounds like, just moving in a straight line from point A to point B. Think about a car driving down a perfectly straight road or an orange falling from a tree straight to the ground. That's linear motion.
Next up, we've got circular motion. And again, pretty self-explanatory, right? It's anything that moves along a circular path. Think about the tip of a fan blade as it spins, or even a planet orbiting the sun. It's constantly changing direction to stay on that curved path.
And finally, there's oscillatory motion. This is that really familiar, repetitive, back-and-forth movement around some kind of central point. A kid on a swing in the park is the perfect example. Or the pendulum on a grandfather clock, just ticking back and forth. It's motion with a rhythm.
So, from something as simple as measuring a table to describing how planets move through space, these two big ideas, standard units and reference points, are the tools we use to understand the world. A spinning planet, that's circular motion. A racing car, linear. A beating heart, that's oscillatory. Motion is absolutely everywhere you look. The only question left is, what kind are you going to notice next?